Problem number 3, air enters in an axial flow turbine with a tangential component of absolute velocity. So this is very important while writing the data. In the yesterday's class, I said the velocity data will be given for two things. One is for fluid and the other one is for the rotor. So here you have the data for the fluid, and this is the tangential component of absolute velocity equal to 600 meter per second, and it is in the direction of rotation. Again, this is also very important. Direction of rotation is nothing but the direction of u, that is the tangential velocity of the blade. Next, at the rotor exit, the tangential component of absolute velocity is 100 meter per second. So at the exit, at the outlet, again they have given the tangential component. So the tangential component here is 100 meter per second, and in the direction opposite to that of the rotation. Again, this term is very important. So the first, at the inlet, it was in the direction of rotation, but at the outlet it is in the opposite direction, that of the rotational speed. Okay, then the tangential blade speed is 250 meter per second. The tangential blade speed is u, and that is 250 meter per second. Now you need to evaluate the change in the total enthalpy of the air between the inlet and the outlet. The change in total enthalpy is nothing but the changes that the energy transfer E. So you need to find out that. And second one, you need to find out power in kilowatt if the mass flow rate is 10 kg per second. So if the mass flow rate is 10 kg per second, then you need to find out the power developed by the turbine, and then you need to find out the change in total temperature across the rotor. So as the fluid expands, its temperature also changes. So the gas or the air entering the turbine will be at a very high temperature, and when it leaves, it will be at a lower temperature. We need to find out the change that occurs in the temperature. So here I'll draw a regular velocity triangle. It's a normal velocity triangle which we had used in the previous class. So this I'll be writing for all the problems. This is for just for reference. Whenever we are solving analytical the turbo machine problems analytically, we need to have this velocity triangle for our reference to find out different velocity components. So I'm drawing that here again, and I'll name them. This is our V1, this is our VR1, and this is U. This is the common base for both inlet and outlet velocity triangle. This is VF1, and this is VF2. This is VR2. A relative velocity starts from the same point, and this is V2. Absolute velocities V1 and V2 starts from the same point here. And the angle made by V1 is alpha 1. The angle made by VR1 is beta 1. Angle made by V2 is alpha 2. And angle made by VR2 is beta 2. So now let us list out the data. The data given in this problem are, first they have given the tangential component of absolute velocity at the inlet. So the tangential component of absolute velocity at the inlet is VU1, and that will be equal to 600 meter per second. And then the second, and then it is in the direction of rotation. So it is toward, if the rotation is towards right, then VU1 is also towards right. Then the next data is VU2. VU2 is given as 100 meter per second, but the direction is opposite to that of the rotation. So this is, if it is towards right, then VU2 is towards left, opposite to that of the rotational direction. Okay. Then the tangential blade speed is given, that is U, which is 250 meter per second. So in this diagram, from here till this point, it is VU1. So this is VU1 and it is in the same direction of U. So both are towards right. And here we have the tangential component of V2, that is the horizontal component of V2, which is VU2, and that is towards left because V2 is towards left. So now we need to find out the total enthalpy, change in enthalpy, that is delta H naught, which is nothing but E. So we need to calculate that. Then we need to find out the power developed if mass flow rate, which is denoted by m dot, is equal to 10 kg per second. And we need to find out the total temperature change, that is delta T naught. So these are the things which we have to calculate now. So this is also a very simple problem. Uh, Here we don't have to find out VU1 and VU2. They have already given the values of VU1 and VU2. So I can write delta H naught will be equal to, we know that from the Euler's equation, energy will be equal to U into VU1 plus or minus VU2. And we know that we have to use plus when both the fluids, both the velocity components are in the opposite direction, and we have to use minus when both are in the same direction. So here, since they are in the opposite direction, I'll write delta H naught will be equal to U into VU1 plus VU2. Please substitute the values and give me the answer. So here U is 250 meter per second, VU1 is 600 meter per second, plus VU2 is 100 meter per second. So delta H naught will be equal to
1,75,000.
1,75,000, and the unit is joule per kg. Enthalpy has a unit of joule per kg, or I'll write this as 175 kilojoule per kg. So this is the change in enthalpy. Now we need to find out the power. So power is given by m dot into energy transfer, or m dot into delta H naught. So mass flow rate is 10 kg per second multiplied by energy transfer, or change in enthalpy, is 175 into 10 to the power of 3. So what do we get here? We get it as 1750 kilowatts. So mass flow rate has a unit of kg per second, and change in enthalpy has a unit of joule per kg. So kg will get cancelled, we'll have joule per second. Joule per second is nothing but watts. So the power is 1750 kilowatts, or it can be written as 1.75 megawatts. So this is the power developed. Now we need to find out the change in temperature, total temperature. So for that, here delta H naught will be equal to 3p into delta T naught. If you remember thermodynamics, so you had studied this equation. Delta H naught will be equal to Cp, that is specific heat at constant pressure, multiplied by delta H naught. So here the working fluid is air, and what is the specific heat of air? Cp of air. Cp of air is 1.005. What is the unit? Kilojoule per kg Kelvin. That is 1.005 kilojoule per kg Kelvin. Now from this I can write delta T naught will be equal to delta delta H naught divided by Cp, so which is equal to 1750 into 10 to the power of 3 divided by 1.005 into 10 to the power of 3. It is kilojoule per kg, so it is 10 to the power of 3 joule per kg Kelvin. What is change in temperature now? It is 174
One.
Kelvin. So this is the change in total temperature of the fluid or the air, and since the temperature of the air reduces as it passes through the turbine, so you can say the change in total temperature or the temperature reduces by 174 Kelvin as the air passes through the turbine. So I'll go to the next one. Here, air flows axially through an axial flow turbine at a mean radius of zero point 0.2 meters. So here we have an axial flow turbine and air flows axially through this at a mean radius of zero point 0.2 meter. If the tangential component of absolute velocity is 20 meter per second, if this is 20 meter per second, then during passage through the rotor, find the power developed by the turbine for a flow rate of 100 meter cube per second. So the flow rate of air is 100 meter cube per second at a point where the pressure and temperature. So at that point, the pressure and temperatures are 1 bar and 27 degree Celsius. The rotational speed, here they haven't given the tangential velocity of the blade. They have given the rotational speed of the rotor as 3000 rpm. So with this data, we need to calculate the power developed in this problem. So first, let us list out the data. The data given here are, first they have given the mean radius. So I'll denote it by small r, and that is equal to 0.2 meter. If the tangential component of absolute velocity is 20 meter per second, at the that is at the inlet, because air is entering at that point. So I'll call that as VU1 will be equal to 20 meter per second. Then the mass flow rate is given in terms of discharge. So Q I will be equal to 100 meter cube per second. And at that point, the pressure is 1 bar, and the temperature is 27 degrees Celsius. Now we need to, and the rotational speed is given. So I'll denote it by capital N, which is 3000 rpm. Now we need to find out the power developed by the turbine. Please analyze the problem and try to see how to solve this. If you look at this statement here, the tangential component of absolute velocity reduced by 20 meter per second, which means to say that as the air passes through the turbine, there is a change in tangential component of absolute velocity, and that change is 20 meter per second. So here it's not VU1, it is delta VU, that is VU1 plus or minus VU2, that will be equal to 20 meter per second. So to solve this problem, first I know that power is given by m dot into u into delta VU, or m dot into u into VU1 plus or minus VU2. Now delta VU is directly given in the problem. I need to calculate m dot, that is the mass flow rate, and u, that is the tangential speed of the rotor. So first let us find out the tangential speed u, and when the rotational speed and the diameter or the radius is given, we know that u is given by pi d n divided by 60, or I can write it as 2 pi r into n divided by 60. Now I'll substitute the values of r and n here. So 2 into pi multiplied by r is 0.2, multiplied by n is 3000 rpm, divided by 60. So this will give me the tangential speed of the rotor at radius 0.2 meters.
62.83.
It is 62.83 meters per second. Okay, now we know u. Now we need to find out mass flow rate. And when the discharge is given in terms of meter cube per second, we know that mass flow rate will be equal to discharge into density, because the unit of discharge is meter cube per second and the unit of density is kg per meter cube. So here meter cube and meter cube will get cancelled. So we'll get kg per second, which is the unit for mass flow rate. So now we need to find out the mass flow rate using discharge into density. So for that, first we need to find out the density of air here. So instead of giving the density of air, they have given the conditions of air, that is the pressure and temperature. So with this, if you remember the ideal gas law, it states that PV equals MRT. We need density. Density is mass divided by volume. Mass divided by volume will be equal to P divided by R into T. Our rho will be equal to P divided by R into T, where P should be in Newton per meter square or Pascal, and T should be in Kelvin. And what is R? For air, R is 287. To substitute the values here, pressure is 1 bar, which is nothing but 1 into 10 to the power of 5 pascals or Newton per meter square, divided by 287 multiplied by temperature should be in Kelvin. So it is 273 plus 27, or you can write it as 300 Kelvin. So from this, find out the density.
1.16.
1.16 kg per meter cube. Okay, now multiply that with the discharge. So mass flow rate is given by discharge is 100 meter cube per second multiplied by 1.16 kg per meter cube will give us the mass flow rate, and that is equal to
116.
116 kg per second. Very good. 116 kg per second. Now we have the mass flow rate, we have the tangential speed of the blade, and we have the change in tangential component of absolute velocity. So we can find out the power. The power will be equal to 116 mass flow rate multiplied by tangential speed, that is 62.83, multiplied by the change in the tangential component of absolute velocity, which is 20. So power will be equal to
145.76 kilo
145.76
into 10 power 3
kilowatts.
watts.
So we are dealing with power, it is kilowatts. So this is the power developed by the turbine. So here in this problem, combustion products approaches an axial flow turbine rotor with an absolute velocity of 550 meter per second. So the combustion products, nothing but the gases, they are entering an axial flow turbine. Generally, the gas turbines are all axial flow turbines. Gas and steam turbines are all axial flow turbines. So here, the absolute velocity, the gas is entering with an absolute velocity of 550 meter per second in a direction of 18 degree from the wheel tangent. So wheel tangent is nothing but, if I draw here, if I draw the rotor or the shaft, this is the shaft and this is the rotor. So the gas is entering tangential to this. The gas is entering at an angle of 18 degree. So this angle is 18 degree. This is the tangential direction and that is entering at an angle of 18 degree. So this is taken as the reference direction, that is the tangential direction is the direction of u, and the absolute velocity of the stream is at an angle of 18 degree, which means to say that it is alpha 1. The mass flow rate is 60 kg per second. If the absolute velocity at the rotor exit is axially directed, which means to say that absolute velocity at the rotor exit is v2 and v2 is axially directed. So here at the rotor exit is v2, v2 is axially directed. So I'll draw the velocity triangle to show that. When the blade speed is 300 meter per second, that is u, tangential velocity of the blade is 300 meter per second. Find the power output and degree of reaction. So we need to find out two parameters here, power output and degree of reaction. So these are the kind of problems you encounter or you face in exam. First, let us list out the data. The given data are absolute velocity at the inlet. V1 is given as 550 meter per second, and the direction of V1 is alpha 1, which is equal to 18 degree. Then the mass flow rate is m dot, which is 60 kg per second, and then the absolute velocity at the rotor exit is axially directed, which means to say that the angle, um, the absolute velocity at the exit is v2 and that is axially directed, which means to say that alpha 2 will be equal to 90 degree. Whenever they say it is axially directed or radially directed, for a radial flow turbo machine, they will say it as radially directed. In both the cases, the alpha 2 will be 90 degree. You need to remember this. And the blade speed or the blade velocity is 300 meter per second. We need to find out the power developed and the degree of reaction represented by capital R. Since we are representing degree of reaction by capital R, whenever they give radius, I'll use small r. For diameter, I'll use capital D. Okay, for this case, I'll try to write the velocity triangle. We have the inlet velocity triangle, which is a normal velocity triangle. There is no change, there is no difference in the inlet velocity triangle. We have the as usual components. We have V1, we have VR1, and we have VF1, and this is alpha 1, which is given as 18 degree, and from here till here it is U. So this is U. They haven't given any condition for the inlet velocity triangle, so I'll write the normal inlet velocity triangle. But for the outlet velocity triangle, they say absolute velocity at the rotor exit is axially directed, which means to say that alpha 2 is 90 degree. So to draw the velocity triangle here, what we have to do is V2 starts from this point where V1 has started. So there I'll draw a vertical line, and then from here I'll join this line. From the starting of VR1, I'll join the end of this line. This is VF2, we know that, and that is also equal to V2 because alpha 2 is 90 degree. So V2 will be vertical in our velocity triangle, and this will be our VR2. So this is beta 1 and this angle is beta 2. So now if you want to find out delta VU, then that will be equal to this length, the horizontal distance between VF1 and VF2. So this is delta VU. That is also equal to, if you observe the velocity triangle carefully, since V2 is vertical, VU2, that is the horizontal component of V2, will be 0. For a vertical line, we don't have horizontal component. And for a horizontal line, we don't have a vertical component. So you need to remember this. Whenever alpha 2 is 90 degree, VU2 will be 0. So delta VU will be equal to VU1. So if you find out VU1, that is sufficient for us to find out the power developed, and then we need VR1 and VR2 to find out the degree of reaction. So let us solve this. To solve this, we can use either graphical method or analytical method. But since we are solving this problem in analytical, now since we are following analytical method, let us solve this also in analytical method. So now I need three velocity components. I need VU1, I need VR1, and I need VR2, and also V2. So these are the velocity components we need to calculate from the velocity from the given data to find out the power and degree of reaction. First, let us calculate VU1. So VU1 is the horizontal component of V1. So I'll take, so if I consider alpha 1 as the angle for this right angle triangle, that is V1, VF1 and VU1 for this right angle triangle, alpha 1, if I consider that as the angle, then this is the adjacent side, VU1 is the adjacent side. So I have to use cos alpha 1. So that will be equal to VU1 divided by V1, which means to say that VU1 will be equal to V1 cos alpha 1. So this will be equal to V1 is 550 into cos of 18 degree. So calculate this,
23.08.
523.08 meter per second. Very good. Now we need VR1. So how to calculate VR1? To calculate VR1, either I need beta 2 or I need VF1. So if I calculate VF1, and if since I know VU1 and U, I'll call this as X. So if you calculate VF1, then X can be calculated as VU1 minus U. Then I can easily use Pythagoras theorem and calculate VR1. So let us find out VF1. And if I take the inlet velocity triangle, that is the side V1, VF1 and VU1, VF1 is opposite to alpha 1. So I'll use sine of alpha 1. Sine of alpha 1 will be equal to VF1 divided by V1. So VF1 will be equal to V1 sine alpha 1, which is 550 sine 18. So VF1 will be equal to, it is 170, 100 and
169.95, 170.
169.95.
okay,
169.95,
is
sir.
very close to 170. I'll write it as 169.95. 9.95 meter per second. And if they do not mention any losses when the fluid is flowing through the turbine, so at the flow velocity at the inlet and at the outlet should be same. So Vf1 will be equal to Vf2, and Vf2 is also equal to V2. So V2 is nothing but Vf1, and its value is 169.95 meter per second. So if they mention any losses, then Vf1 will not be equal to Vf2. So we cannot use that relation. But here, since they haven't talked about any losses, we can consider Vf1 is equal to Vf2. So now I know Vu1 and I know V2 and Vf1. Let us calculate Vr1. So to calculate Vr1, I will apply Pythagoras theorem. So Vr1 will be equal to root of Vf square, Vf1 square plus the value of x here is Vu1 minus u whole square. So this is equal to root of Vf1 is 169.95 squared plus Vu1 is 523.08 minus u is 300 whole square. So what is the value of Vr1?
280.44.
280.44 meter per second. Can we calculate Vr2 now? Again, I will apply Pythagoras theorem. Vr2 will be equal to Vf2 square plus base for this triangle is u. So it is u square. So that will be equal to root of 169.95 squared plus u2, u is 300 squared. So Vr2 will be equal to
344.79.
344.79 meter per second. Now we know all the velocities. Now let us find out the power and the degree of reaction. I'll go to next page. So power is given by m dot into u into Vu1 plus or minus Vu2. But in this case, we know that Vu2 is 0. So it is just m dot into u into Vu1. Now let us see the values. They have given m dot as 60 kg per second, u as 300 meter per second, and Vu1 is 523.08 meter per second. So it is 60 into 300 into 523, oh, 523.08.
9.4 megawatt.
941.5.
9415 kilowatts or 9.415 megawatts. So this is the power developed. Now we need to find out the degree of reaction. So the degree of reaction is given by static component divided by static plus dynamic component. So here static component is Vr2 square minus Vr1 square divided by the dynamic component is V1 square minus V2 square plus static component is Vr2 square minus Vr1 square. So now substitute the values. What is Vr2? VR2 was 344.79 meter per second. That is 344.79 square minus VR1 is 280.44. So it is 280.44 square divided by V1 is 550 meter per second. So 550 square minus V2 is equal to VF1, which is 169.95. So 169.95 squared plus 344.79 square minus 280.44 squared. So what is degree of reaction here?
0.128.
0.128, and this has no units. The degree of reaction is 0.128, or you can say it as 12.8, or approximately 13% of energy will be transferred in the form of the static component, and the remaining energy will be transferred in the form of dynamic component. So I'll be taking um, a few more classes for solving problems. So in another one or two session, I'll solve analytical method problems, and in the remaining sessions, I'll solve graphical method. So please try to follow this, and please practice these methods. Otherwise, it will be very difficult for you in exam. So example, in turbo machine, around 40 to 50% will be theory, because you have very less theory, and theorinal ಜಾಸ್ತಿ ಬರದ derivations. The remaining 60 to 50% will be problems. And this time we will be conducting exams for all semesters. So you have to face exams, and you have to solve these kind of problems in exam. So please try to concentrate. I'll stop the session here for today's session.